I was on the wrong slide. It's still about these two things, though. And we have been working on integral calculus in the last month. So you know how fast something is changing, and you want to know how much of it there is. So, how is it that we know how fast something is changing? What have we started with that tells us how fast a quantity is changing? Rate of change function, right? A rate of change function. And on Friday, we looked at this sand unloading, right? And that was our rate of change function. And what is it that we were trying to determine that's going to tell us how much of it there is? What's that? So our end goal is how much of it there is. How do we represent that? With what? Accumulation function. Not just accumulation, a function, right? So given any time that's gone by, we want to know how much, what the weight of the scale, what the weight is showing on the scale. Okay, so a function is the most powerful thing you can have because you can pick any time and it'll tell you what the weight is in that example, right? Okay, so the question is, how do we get from point A to point B? And that's what we've been constructing laying down all the foundation to get from point A to point B. And what did that journey look like? How did we start this journey to get from a rate of change function and determine the corresponding accumulation function? Okay, linear, what was that?
Steps.
Right, a constant rate step function. This is how we start. And we define that as step x, and the one we used the most was r of left of x. That was the one we used the most, and that's what's being shown here. And then where do we go from there? What does that allow us to do? That step function then allows us to? Yeah, we can get accumulation because now we have constant rates. So we're going to sum up bits of change as k delta x plus k delta x. Each k delta x is a bit of change, and we're going to sum those up. And as we sum, we keep track. And so we built a function, right? We built our accumulation function, a of x. And that's what we saw on Friday, the one that's kind of purple there that I've labeled a. Piecewise linear accumulation function, which comes from the step function. So there's one step left, and that's how do we get from, now that we have this approximate accumulation function, we want the real one, we want the actual one, because we know that's approximate. It's based on a rate of change function that's not accurate, because it's made up of all these constant steps that doesn't exactly match the rate curve. So how are we going to get that true accumulation function? This is the last part of the deal. So let's go back and look. So there's our rate function. That's the first thing. We start with an exact rate function. And what do? Step function. From the step function, we can get the accumulation function. So how are we going to get this exact accumulation function? We're so close. We're so close. How do we get the exact accumulation function now that we have the approximate accumulation function? So, what's that? So some of you are getting it. So if we make delta x smaller, what will happen to our approximate accumulation function? We'll get better. Let's watch it. So here's the deal. So all these functions here, none of this in GC is out of your grasp because we've done it all. Look at the functions. Do we do that function? Do we do that function? Step equals r of left? Yep. Do we do this function? Okay, so those are the functions that we've graphed. We've graphed the original rate function, the step function, and then this accumulation function, the approximate, the piecewise one here on the right. So what I'm showing here is all within your grasp, and you've actually been doing it in your homework. So because all of those functions were built on these varying variables, parameters, I've got it based on delta x. Instead of having delta x be a constant, I've made it a slider. So now I can just choose a better value of delta x. And what happens to the approximate accumulation function when I do that? Did you see what happened? So what happened? The step function got better. It's doing a better job. And then now the approximate accumulation function is better. Even better. So here my delta x is 0.19. 0.19. Here's 0.08. So this is the power of graphing calculator, that we can write those functions all in terms of a and x and delta x, and all we have to do is change delta x, and the picture shows 1,000 words. Okay. So now if I make delta x even a little bit smaller, and I turn off the original rate function, what do you see? Now I've got the step rate function, but I don't have the original rate function. How's it looking? It's looking like very close to that original rate function. All the way to, here's 0.005 for delta x. So that you're still looking at the step rate function, but delta x is just really, really, really small. And when you do that, then you get an accumulation function that the approximate one converges on the real one. This is so much better than you think. I hope you're appreciating this, what you just saw. Okay? See it again. Because we've been living here, right? We've been living here for months trying to figure it out, trying to understand it. And all it takes now to start doing calculus is make delta x smaller. That's calculus. Calculus is all this stuff we've been doing with very, very small delta x. That's calculus. So we've laid all this foundation. We really weren't quite doing calculus yet. We just did it. So now when you think of extremely small values of delta x, you get a virtually accurate rate graph from the constant step graph and a virtually accurate accumulation graph. Okay, so I hope that you try to build this file. So you have most of the pieces from your homework and the things we did in class. You have most of it, so you can recreate this. Okay, back to this. All right, so what we're talking about now is to do calculus, we need to fine-tune our accumulation. That's what we need. Okay, so here's our approximate accumulation function, which is essentially just summing up a bunch of k delta x's, right? We got all the full intervals on the left, and then that small partial interval there on the right. But all of it's the same. It's just keep adding up. K delta x plus k delta x plus k delta x. Okay? So now we just take that same equation for our accumulation function and make delta x very small. And so we use the terminology dx. That's called the differential, dx. It just means like at the molecular level. Or at like the distance between atoms. That's how small dx is, like how far it is between atoms. Okay? And so then you just have the same function, but everywhere there's a delta x, you just think of that delta x as being microscopic or viral. Okay? And essentially, it's the same thing. We're just summing up a bunch of little bits of change, but then they're just really, really small bits of change. Okay? So this version of the A function with really, really small delta x, or dx, we have a simplified notation. Okay? This notation means the same thing as a of x with a very, very small dx. So this is called integral notation. And we read it, the integral from a to x of rt dt. Okay? What does it do? It outputs the accumulation of a quantity with rate function r as x varies starting from a to the current value of x. So it's exactly the same as this. Let me just make sure you understand. It's exactly these two functions are virtually the same. They are the same. They are the same. When you have a very, very small delta x, our approximate accumulation function, we use this notation to simplify things. Okay, so this is what an integral is about. So let's see what are the similarities between the notations here. So what do you notice that's the same about this new notation and the old accumulation function? What do you see that's the same? Okay, R. Yeah, so if this whole thing is really just like this, right? So we know we're taking R times change in X, R times a change in X. So we got the R, so we got the rate right there. What else? So there's our rate. How do we calculate accumulation? One little bit of accumulation is K delta X. Do we see that here? Yeah, right here. So this is one. It's like an infinitesimal bit of accumulation. Based on the rate function R. Okay, it's a small bit. What else do we see that looks the same? What do we do with those bits? Add them up. And so this is Greek sigma, which means sum. Greek sigma means sum. We have a different symbol here. This is German S, which also means sum, but just summing a lot more things. So the integral symbol is a German S, and it just stands for sum, the way that sigma stands for sum. It's just that the German S is like, means sum up a gazillion things, right? Yeah? How does that take into account partials? So what happens, so let's think about that. So the partial interval is just a smaller version of the delta X intervals, and what's happened to the size of our interval? Yeah, so they're like all the same, right? So when they're like all virtually small, so there's no difference between part of infinitesimally small, right? So they're like all the same. What else do we see in that notation that's... Yeah, so A means what? Starting value of, is it X or Y? Is it input or output? Input. So this is confusing. Sometimes students want to put output values here. This is the starting value of X for where we start accumulating. And then what about X? Obviously, it's an X value. That's the current value of X, right? We said we started A and we're constantly increasing X. We could pause, and we have a current value of X. That's where we stop accumulating at the moment, right? So at the moment where we're stopping accumulating. Okay? So this is a function. See, the output is an amount of accumulation, and the input is what? So what's determining how much accumulation we get? What's determining how much accumulation we get? Right? Which is what?
Where we currently are.
What's it?
Where we are with X.
Yeah. Okay, so yeah, where we're going to stop accumulating, right? So the X, the input, is like the left side, right side of the interval over which we're accumulating. So A is fixed, and then we've let X vary. So then the output is the accumulation for every value of X here on the right. Okay, so some of you have a question. You're looking at this and you have a question. What is your question? Why is there a T? Is that it? Yeah, she said it. I knew it. So, why is there a T? So let's check that out. Let's go back to GC here. Okay, so down here. Oh, so then, so when to graph, when I started here, I showed the exact and the approximate, right? Let me just put that up. Okay, so there's an approximate value of accumulation and the exact. So how did I graph that exact? Well, you can graph integral expressions, integral functions on Graphing Calculator. So to get integral notation on Graphing Calculator, Control-Shift-I. And so here's what I graphed in black there on the right. fx equals 0 to x rt dt. So based on the rate function, the red one that I'd already defined, it's now making a new function, capital F, from 0 to x of rt dt, and that's that black one that I'm graphing on the right. All right, so let's think about if I were to put 1 into this function, I get a value, 2.41026. What's the meaning of that? When I plug 1 into that function, I just got 2.41026. So have a 30-second conversation with the person next to you. What does that mean? F of 1 equals 2.41. Talk to the person next to you. Is that a question? Okay, let's give it a shot. So f of 1 equals 2.41. What does it mean? F of 1, 2.41. What does that mean? Someone in the back. Can you tell me? I don't know. Who's? Okay. What does it mean in context, though? In context. Can you say it in context? Like what we're.
Starting at 0 and then going to the cancel value of 1 and 2.41
Okay, so but we want to talk about time and sand and rate and all these things right in front of them.
Okay, so this would be the accumulation of the sand unloaded on the scale from the time of 0 to 1 second.
Right. That was pretty good. So at 1 second, this is the weight of sand on the scale. It's the accumulated weight of sand on the scale at 1 second. So I can come over here on the. You can't really read that too well, but you can click on a curve and you get crosshairs and it gives you ordered pairs right there. So it's telling you x equals 1, y is 2.41. That's how much weight of sand is on the scale after 1 second. That's what this accumulation does. Is it exact or approximate? I've heard both. You better know. The curve is based on big chunky delta x's or infinitesimally small. Very, very small. This black curve, which is the capital F function, the integral function, is representing exact values of accumulation. Okay, so now we ask the question, why do we need that t? So here I've defined. Anybody have a question? So here I've defined g of x as just no t's, just all x's. 0 to x, r of x dx. And I'm going to do g of 1, okay? Will it be the same or different? What would g of 1 mean? So let's write out. What would the expression g of 1 mean? Can I rewrite this expression for g of 1? I should not say it's equal to. So if we had g of 1, it would be the integral from 0 to 1 of r of 1 dx. Dx just means they're a very small interval. It's not d1, right? So dx is very small. Okay, so is that the same or different? We need to accumulate from 0 to 1. Over that 0 to 1, is the rate constant or is it changing? Changing rate. What is R of 1? That is a single rate. It's the rate at 1. So what we just did, if I come over here and click on over here, what I just did was 4.88. This is essentially the same as 0 to 1 of 4.88 dx, or a constant rate for that entire interval. So is g of 1 going to be greater or less than f of 1? It's gonna accumulate from 0 to 1, but all at that the peak rate, the 4.88 rate, the whole time. So will it give a too high of a number or too low? Too high. So if I come over here and do g of 1, 4.88. Okay, turns out to be 4.88, which is not accurate. We want to accumulate at the changing rate . There we go. So we want to accumulate at this red changing rate from 0 to 1. So we need to introduce a new variable t, because x stands for where we stop, at the end. So we need in between, we need a variable that's going to vary from 0 to 1, or 0 to wherever we're going, 0 to x. A different variable. It's still x values, but it needs to change so that we get the effect of the changing rate between 0 and the final value. If you do 0 to x, rx dx, then you just took the rate at the end of the interval and made it a constant rate over the whole thing. See? That's what happens. So you don't get the right result. Yeah.
So is t like a slider in memory calculator?
No, it's just a placeholder. It's just a placeholder that's going to take on every value of x between 0 and the current value of x, so that we get that changing rate from there to there.
So you're saying don't ever use right?
Okay.
A g function. Don't ever put actually.
If you're trying to write the accumulation function for the changing rate, you cannot have these two symbols be the same. That's what I'm saying.
Okay.
If these two symbols are the same, then you're going to take the final value of accumulation and end up plugging it in there and getting a constant rate for the whole interval. And you don't want that. So we need a new variable that gives us that changing rate that we want. Okay? Any other questions? Dx. So for each one, determine if it's a valid accumulation for its rate function. Okay? So is it doing what we were intending it to do? Okay? Then identify all the parts by their meanings. Okay? Then we want to kind of rewrite these as functions to see if it's a function, actually a function of x, or a particular output of the function. So we want to represent it that way, based on whether it's a function of x, meaning that that right side could change, or is it a particular output value? We're picking a right side. And then describe the meaning of the expression as a whole. So we've got about 3 minutes. See how it goes. So work with the person next to you. Try and make sense of this expression. Okay, start. First one, F1, F1, capital F1. Is it a valid accumulation function?
Yes.
Yes. And is it a function or a particular output? It's a function because the input is our final value of x. Okay, so happy face, right? That's good. What about F2? No. Okay, it will give you, that is a function. It's a valid function, but it's not the intended, because anytime you have the last value of x, that's going to be, you're going to take that rate as a constant rate the whole time. So this is, it will give you something, but it's not what we want, right? It's not what we're trying for. We want that rate to change over the interval. Okay, how about this next one? Is it cool?
Yeah.
It's good. Everything's good. Starts at A, goes to x. What is 2v minus ln of v plus 1? What does that represent? 2v minus ln of v plus 1. This is a rate of change function. That's a rate of change function. Okay, how about F4? Ooh, dissension. Good or not? It is okay. It is fine. Is it a function or a particular output? So this is a particular output. So we wouldn't write it f of x. We would write it as f of 8. Doesn't make sense. We're actually, it's like there was a function there, and they plugged 8 into it. They said, there was this function, accumulation function, and we said, we're going to stop at 8 and get that amount of accumulation. So is this thing, is this a number, or some other function, or something else? Is it a function or a number? It's a number. It has a changing rate function in it, but it is the amount of accumulation starting at 0, ending at 8, at that rate. That's a value. That's a number. Okay, so this is a little bit different than what you're used to. This whole thing is a value. The amount of accumulation starting at 0, ending at 8, at that particular rate. Okay? What about this one? This is an output also. It's f of 15. For some function from 10 to x. For some function from 10 to x, this is f of 15. What about the last one? What about, but it's got t's and dt. So it's okay, right? No, the problem is that this is the same as this. That's the problem. You get it? It's not just about x. It's about the fact that these match. These match. Then you're going to plug something in, and then you're going to plug it in there and get a constant rate. You're going to get a constant rate.